Hello. This is our machine learning for Virginia project, and we are predicting life expectancy. This project, research, and presentation was done by Josh Devera, Bryant Chow, and Tony Lay. So, the Virginia Department of Health Office of Health Equity has developed the Virginia Health Opportunity Index to help communities understand factors that contribute to people's health. This index gives insight into how communities can put in a conscious effort to improve health outcomes for their residents. The HOI is a composite measure of the social determinants of health. The social, economic, educational, demographic, and environmental factors that relate to a community's well-being and the health status of a population. U.S. Centers for Disease Control and Prevention estimates that more than half of the variation in health outcomes is driven by the SDOH. Understanding Virginia's HOI is important, as it gives us insight into which socioeconomic factors that these communities should invest to improve their overall health. Given this information, the government can also act to invest in these factors. Ultimately, the upward projection of health in Virginia could also attract more people to the state.
In order to process our data, we use techniques such as one-hot encoding and imputing to create numerical values to be used in several machine learning models. We collected two datasets, one with data for the Health Opportunity Index and the other with data containing life expectancies. Both datasets included numerical values called census tracts. These numbers indicated the geographical location and time that the data was surveyed so they could be used to match the data between the two datasets. The census tract was 11 digits, the first two digits indicating the state, the next three digits indicating the county, and the last six digits indicating the part of the county and the moment that it was collected. For our Health Opportunity Index data, we collected indications to further differentiate between geographical locations. First, we had whether or not the location was rural or urban. Furthermore, we had different profiles which used their own indexes to measure different health aspects of a community as seen on the tree. For example, economic opportunity profiles include indicators such as employment accessibility, income inequality, and job participation. With initial preliminary correlations, we saw that some of the major indicators were affordability and education, as they had the strongest linear correlation with life expectancy. This can be reinforced by the third graph as shown, which shows that the consumer opportunity profile, which both of these indicators belong to, also had a strong correlation to life expectancy. For our approach, we referenced a similar project where the Health Opportunity Index was used to predict life expectancy by census tract in Ohio. This is created by the National Institute of Health. Using this as a baseline, we collected more specific indicators and followed a similar procedure using multiple ML models such as linear regression and XGBoost. The most simple model that we created was a multivariate linear regression model. This model had mediocre predictions and had a moderately high RMSE. This could potentially be because of such a simple model as linear regression struggles with categorical data, such as our rural-urban data.
The next model we decided to use was the decision tree. A decision tree is a form of ensemble learning, which uses multiple different models to find the best parameters for the model. Because of this, the decision tree is able to find more abstract features and trends in the data, unlike linear regression. As you can see, there is a lower RMSE of 9.7. However, we wanted to get the RMSE lower since life expectancy ranges between 0 and 90 years. The next model we decided to use is random forest. It acts like the decision tree, but instead uses multiple trees to find the right parameters. Hence, it is a forest. This model allows us to find deeper trends and create more accurate models, as seen here. We also performed a grid search to find the best parameters. The best parameters from our grid search yielded 12 features and 25 estimators. As a result, the mean RMSE for this version, or for this model, it was 2.27 years, which is pretty good. The true life expectancy versus predicted life expectancy shows a pretty linear graph. However, we decided to go on to one more stronger model. The last model we decided to use was the XGBoost regressor, which stands for Extreme Gradient Descent Boost Regressor. This basically uses the concept of gradient descent, but faster because it uses trees. This is also a boosted algorithm, which means the outputs within each training layer become inputs within the same layer, and that is eventually passed on to another layer of the tree. Because of this, the XGBoost regressor dynamically determines the weights during training and allows us to form an even more accurate model. Here is an image of us optimizing the XGBoost regressor. We performed a parameter search on the objective function, which is squared error, the number of estimators, the max depth of the tree, as well as the learning rate. On the right, you can find the results of our grid search, and the best parameters were a learning rate of 0.25, a max depth of 3, 30 estimators, and the objective function, which was the regressor squared error. Here are the final results of our XGBoost. It yielded the lowest RMSE with a value of 2.14. It also ran quicker than the other models because it used an extreme gradient descent, which allowed it to calculate a lot faster. The RMSE in this model is comparable to random forest because of the similar tree structure found between XGBoost and random forest. Here's a graph of the final results of our best model. It shows true life expectancy versus predicted life expectancy, which has a pretty linear trend.
The models we created throughout our experiment have shown that the HOI is a valid indicator of life expectancy. Our best model, XGBoost, did not have weights, so it is difficult to associate weights with specific factors in the HOI. In general, with more resources, we would be able to associate costs with specific factors of health in order to improve Virginia life expectancies with the lowest cost possible. These models could be further improved to use trends in the health indexes to predict life expectancy in future years. And these are the data sets we used. We had one for Virginia Health Opportunity Index, Virginia Life Expectancy, and US Census ID forms. This work has been a part of the Machine Learning for Virginia project at the University of Virginia.